So GTAR, it's a team of undergraduate and graduate students more often than not, and we compete in competitions all across the globe. We're predominantly aerospace engineering students, but we welcome everybody. I think we started competing in about 2008. We've competed in pretty much any competition that we can get into, so we've done a lot of IRC work. Won, I think, Mission 4 or Mission 5, I can't remember, the 2008. We've competed in the IMAV competition, and recently the American Helicopter Society started a competition, MAV Challenge, I think 2014, and we've been competing in that every year as well. I'm also going to talk about some of this other competition work that we're doing, and it'll make more sense in a couple more slides. So two competitions that we're currently also working on is this MDZIRC. It's a competition hosted in Abu Dhabi. Grand challenge is $1 million, which is pretty good motivation. We're possibly looking for partners as well for it, because it's a pretty, there's a couple challenges to this. And then this summer we were also working on the DJI Developer Challenge. Unfortunately last week we didn't make the final 10 team cut, but I'm going to talk a little bit about both. So the MDZIRC challenge, it's 3 challenges, and the grand challenge is to do all 3 in 30 minutes. So the first challenge is to land on the back of a moving truck. The truck has a target on it. It's pretty much just a circle with an X. The truck has a speed profile, and it kind of does like a infinite loop pattern. It's also outdoors, so I guess we have GPS, which, as talked about earlier, it's a lot easier than when you get indoors. Challenge 2 is we have to locate a panel with a ground vehicle and determine which wrench we need based on this valve stem, and then rotate it full rotation. And then the third challenge is to grab static and moving objects on the ground and place them into different receptacles. Collaborative lifts are possible but not needed. Yeah, as I said, it's we have to do all 3 challenges in under 30 minutes. That's kind of the general goal. And then for the DJI challenge, somewhat similar to that first mission for MDZIRC, is we have to take off from a moving Ford F-150 and then go into kind of like a office environment and search for survivors, which is April tags. And April tags are kind of like a QR code. You've probably seen those before. And then relay that information back to the Ford F-150. And then once you've completed that, you're supposed to land in the back of the Ford F-150. So I guess why I thought that would be kind of interesting for why to talk about it is because a lot of those goals for those 2 competitions, they have a lot of interweaving things that are needed for IRC. And without a doubt, the IRC is a much more difficult competition. One is because it's indoors. So the other 2 competitions are outdoors, so we have GPS. Not as much autonomy is needed. There is some obstacle avoidance, but not to this level. And again, I guess there are 2 ways for the IRC is to either land on top of it for the magnetic thing or land in front of it. And so that technology is needed for this competition as well. So I thought I'd first start off with our goals for this year. This is our first attempt at Mission 7. Our goal is to take off and navigate the arena, more than likely above the obstacles. I'll talk a little bit about that. We don't have any way currently to detect the obstacles, but we have target tracking software that I'll talk about briefly. We plan to detect the Roombas and try to get information with a particular Roomba that we pick, and then initiate a landing on top of the Roomba and possibly repeat. The GCS operator, so the ground station guy, will stay in the loop, meaning that the vehicle will be flown semi-autonomously, so I will or someone else will kind of give waypoints to the Roomba or to the vehicle to fly. So it won't be manually flown at all, but it will be flown by the computer, but someone will be guiding it. And the reason why we're doing that instead of having it fully autonomous is we still really don't have any idea how to do it. We developed some simulations to test target tracking software and different strategies and obstacle avoidance. And even with perfect knowledge of the arena and every single Roomba, we can't even get close to completing at a 100% rate. We've tried different strategies, and our current best strategy has a 25% rate of success. that's with perfect knowledge of everything. That's the reason why we haven't done any mission manager stuff, is because it just doesn't, I don't think it makes sense for us yet to implement, because we won't have perfect knowledge of anything. So we decided just to work on the tasks that are a little bit easier. And I guess the current strategy that we use is, so any of the Roombas that are heading away from our goal, that are closer to the goal line, we kind of try to navigate them back towards. We've tried different strategies where, like, any of the Roombas that are about to leave the arena, we would put that into the arena. But this is by far the best one that we've had. And this 25% rate is based on 1,000 simulations. So our target tracking software, it's pretty good stuff. It can track multiple objects at once. We run 10 extended Kalman filters simultaneously, which propagate estimates, and they determine if the measurements are converged on a target or not. Based on which kind of things we're tracking, we use different classifiers, I guess, for the tracking. So hard classifiers are a machine-based learning technique where you provide it with a set of images. I think it's like 500 positive images and like 600 negative images, and it kind of goes through this thing and develops this class for detecting. Another method that we use is template matching, where it's much simpler, where you just give it kind of like a little picture with maybe like a circle or something, and then based on the camera feed, it goes through and tries to match to see if there's like a correlation between the template and what you're seeing in the world. And then April tags is that QR code that I talked about briefly. So for our navigation, we do everything visually. So in our navigation filter, we track, or we maintain the position, velocity, attitude, and then bias states for the accelerometer and gyro. And we also track features from the camera. So I guess this picture, we typically track 16 three-dimensional features on the ground. And that gives us kind of our it's more of a relative positioning system, because we don't have GPS, so everything's kind of relative. In our navigation system, we use a Bierman-Thornton EKF. The reason we switched from an EKF to a Bierman-Thornton EKF is because typically for visual SLAM especially, you run into a lot of problems with diverging solutions due to like bad initial estimations and poor models. And the EKF also underestimates your covariance and how well you're doing. And the Bierman-Thornton EKF is a lot more numerically stable. So with the Phu-Van EKF, your covariance P matrix, it's encoded into this U and D, which U is just a upper triangular matrix, and D is just a standard diagonal matrix. And I guess this paper, if you're interested in that, you can read more about it. I don't want to get too in-depth into it. But with this system, you have to reformulate your update and propagation steps. And I guess, as I said, we track 15 vehicle states and then 16 three-dimensional feature states. So this was the vehicle we were going to use up until about a week ago. And that was mainly because of some of our, we only have 3 members right now. So a lot of us were working in the DJI competition until we got booted from it. And this is a vehicle that we've used in the past for other competitions. It's called our GTQ Mini. It's a 500-gram vehicle that we developed for the American Helicopter Society competition. And that one, it's more focused on a little bit more on design, where they put a limit of 500 grams on the vehicle. And so everything had to be really shrunk down for this one. And I guess the basis of that competition was to take off from a helipad, which you see there, and then locate vision navigation again, locate another target in the arena, and then hover over it and then return back. And I'll show a little bit of video of that during the questions. So I guess with this, the last week we developed a larger size vehicle, and the main reason for that was because when you shrink everything down, the flight times gets dramatically decreased. So one of our members does a lot of vehicle sizing and optimization. And I'll talk about his tool. And with this tool, we kind of were able to size a vehicle that's a little bit larger for a longer flight time. And that also, I guess, for future competitions that we plan to do with IRC, it'll allow for more integration with other things like obstacle avoidance and better landing gear as well. So this is kind of our architecture currently. It's very similar to what you guys just recently saw. So we use a Gigabyte Bricks as our main computing software. It's pretty much just like a very small desktop machine. As far as sensors, we have a downward-facing camera for target tracking and then visual navigation. A Terra Ranger Luno, which is an altitude sensor. It actually outputs at 600 hertz, but we do something to it and then output it at 100 hertz just because we don't need it at 600 hertz. And ArduPilot is our sensor board and also kind of like our manual flight operation board, and that's open source board. We wrote custom firmware for it, so it sends all sensor information to the Gigabyte Bricks for processing, and then you send back from the Gigabyte Bricks motor commands, which get out when you're not. And then on board, we run the GAF updates for the features at 50 hertz, and 100 hertz. We have the ability to do trajectory generation stuff, and all our flight control happens on there, and then our target tracker as well. We have an onboard Wi-Fi router for 5.8 gigahertz. We recently switched from 2.4 because it was running into a lot of problems, and then just their safety pipe. So what I mentioned briefly was the vehicle sizing. One of our members developed an online tool, which I encourage anyone that's interested to go to the website. What it allows you to do is it allows you to enter in vehicle parameters that you currently have or you're thinking about. Anything regarding the vehicle, so like your motor size, propeller size, battery, takes into account the weight for different propellers, and it allows you to estimate the range, the endurance of the vehicle. Another real nice benefit is it does sensitivity analysis, so you can say for instance you're currently flying with a 4,000 milliamp battery. Like, what if I change it from 4,000 to 5,000 or 4,000 to 6,000? It allows you to do that, and it takes the battery weight account, and it allows you to more easily size your vehicle. And I'm going to switch to the video for questions. And then I'll take any questions, I guess, while this is playing.
So the cloning configuration that you're talking about with your vehicle?
Yes. I guess I didn't mention it, on our vehicle we have a Vicon bulb, so there's a room in Georgia Tech. It kind of provides like an indoor GPS monitor along lines, and that kind of we use just to tune the vehicle, and so that's where we did the majority of our flying, but we've done vision-based navigation. And I guess the computer and sensors are actually pulled off of this vehicle flying right here. So this is our ground station like operator. So typically, I guess I didn't record the video feed, but all like those dots are kind of features on the ground. And I guess with this system, since we don't have like a global reference, there's a lot of drift involved in this kind of stuff. So this was kind of just a mission profile that we told the vehicle to fly initially. And I guess on the way back, we'll see where the helipad's supposed to be and where it actually sees it. And I think we had like 10 feet of drift. And that was more along the lines, well, we expected some drift, but a lot of it was due to the camera. Since the frame is so small, the camera was actually mounted to a piece of balsa, and the balsa kind of was rotated. So the camera was like tilted 10 degrees when it should have been flat. So it kind of created some of that extra drift. So basically tomorrow, instead of it being fully autonomous, I'm going to pretty much tell the vehicle where to like fly. So I'll give it like a waypoint out in the middle of the field, and hopefully our target tracking software is going to work. And then if it sees a target tracker, like you're going to see this green circle on the ground. And then I'm going to switch the waypoint to the information waypoint. And from that point on, it'll just track that green circle wherever it goes. And then if that's working well, we're going to change the formation waypoint to a land waypoint or a landing. We've tested that with some of those other competitions that I talked about earlier, where the DJI, where we landed on target. But we haven't tested that on a moving rover yet. one other thing to mention is, so our vision navigation software works a lot better with a really wide field of view camera. And one thing that we noticed in this last week of testing is by using a really wide field of view camera and flying above these obstacles, the amount of pixels on the target is a lot less than what we really want, and the target tracking software doesn't work as great when you don't have a lot of pixels. And we thought about switching to a narrower field of view camera, but when you do that, anytime that if you have like a really narrow field of view, if the camera rotates at all, the features are going to get moved a lot more, and it's going to be a lot harder for our vision navigation to track that. So kind of like a design trade-off. And I think next year we'll probably add another camera. We just ran out of time.
I did have one question for you. You did not show your method that you're going to provide for terminating the vehicle.
So I guess our current method of flying is we have the mode switch for manual to auto, and so that the safety pilot, all he has to do is switch from. So I guess we're going to have to do some more testing tonight, unfortunately, but I don't know if we're going to do auto takeoff or not. But I think our idea is to, I guess our backup plan would be to take off in manual, flip into auto mode where then it would hover. And I guess our general fail-safe, there's two fail-safes. One would be if the vehicle were out of control, it would just switch to manual, and the onboard computer would get kicked out and you're just manual control. And then I guess the other mode would be to actually turn off the radio, and the fail-safe kicks in and it just falls. But I guess we've never tested that to the extent because we don't want to crash.
How can we get
At KSU,